Assalamu alaikum. Welcome. My name is Mishini Shai, and it is my great pleasure to welcome you to this event as professor at Khalifa University and as director of the Distinguished Speaker Series on Science, Technology, and Society. Last month, many of you joined us for Professor Hans Schenhuber's lecture on the impact of climate change. And next month, we will be presenting another very distinguished speaker, Christina Johnson. She's a very highly accomplished scientist who recently served as United States Under-Secretary of Energy in the administrations of President Barack Obama. And so I want to use this occasion to publicly announce Dr. Christina Johnson's lecture, which is called An Economic Plan for a Clean Environment. So she will be delivering this very lecture in the same venue at ECSSR on April 11th at 7:15 p.m. So I hope that all of you and even more of you will join us once again here in this room just a few weeks from now. So please write that down and mark your calendar. Tonight, as speaker, Richard Resnick promised us to wake us up to the genomic revolution. Both the subject and the speaker are bound to energized debates. This talk could not be more timely. I don't know if you all, some of you have read last week New York Times article, which was reporting on the enormous drop of cost of the gene sequencing and the dramatic medical advances that it is bringing within our reach. So the scientific and technological revolution he will be talking about great promises with profound, at the same time, profound ethical questions. And I hope those will be addressed today, including the implications of being able to change our genes, I don't know if we'll go that far, and the questions of who will have access to the benefit of greater health and longevity. In other words, Richard Resnick focuses on the genomic revolution is central to the vision behind this speaker's series, which highlight critical issues linking science and human society. So I want to note here that Khalifa University President Dr. Todd Lawson and our Executive Vice President Dr. Arif Al-Amadi both really deserve great credit for supporting and promoting the public dialogue inspired by our Distinguished Speaker Series. It's a dialogue that Khalifa University is proud to join with the broader community. So with further no delay, I would like to ask one of our Khalifa talented student in bioengineering, Noura Al-Matrousha, to introduce President Lawson, followed by a few words from our colleagues, Professor Steve de Weerth, who is the chair of biomedical engineer, and will introduce our speakers and moderate the discussion following this talk. So thank you for coming. And before I just let Noura introduce Professor Lawson, I will just ask you kindly to turn off your cell phone. I see signs in the back reminding me of that task. So thank you very much.
Assalamu alaikum. Good evening, ladies and gentlemen. My name is Noura Al-Matroushi, and I'm a biomedical engineering student at Khalifa University. It is my pleasure to introduce to you Dr. Todd Larson, President of Khalifa University. Over the past 28 years, Dr. Larson has contributed greatly to a variety of fields, including mechanical, civil, environmental, and biomedical engineering. His research contributions, combined with his vision, make him a great leader for Khalifa University since he arrived in 2010. His efforts have moved us from being just a newborn university to a rapid developing community whose students are motivated to participate in local and international competitions and collaborations. Dr. Larson strives to listen to the students' thoughts and concerns and tries with the help of our diverse faculty to enable them to achieve their goals and to broaden their educational and social experience. On behalf of Khalifa University students and faculty, we would like to thank you for your continuing efforts. So without further ado, please join me in welcoming Dr. Todd Larson.
Thank you very much, Nora, and good evening, everyone. It's a pleasure to be here. I'd like to welcome everyone from the Khalifa community and from Greater Abu Dhabi to the Distinguished Speakers Series. Tonight, as my colleague Micheline Ishai has pointed out, our speaker is addressing a question of tremendous importance. He's really going to look in particular at the implications of the genomic revolution and what consequences that may have, both within the medical and technology world, but also how that interfaces with the society at large that we're in. And I think, as many of you will realize who have attended previous lectures, that's very much the theme and the intent of this series. We are a technologically oriented university. Currently, our offerings are primarily in engineering, and we're expanding into areas like international and civil security. Many of you may be aware of that program, as well as our evolving efforts in the area of medicine. And with this focus, obviously, these implications of the technical work that we do and how they interface with the society in which we live are really of importance. And this is really the theme and the question that we would like to explore in different technical contexts throughout this series. I would like to add the thanks, my thanks to those of my predecessors, to ECSSR in particular. I was speaking with some ECSSR folks earlier this evening, and this partnership between Khalifa University and ECSSR has really been tremendous for us, and we trust for ECSSR as well. It's enabled us, I think, to better reach our goal, which is to really engage the community in these broader issues. And so we're very grateful for that partnership, and I'm sure we're all grateful to have such a wonderful hall in which to hear these lectures. So I think at this point, much has been said already about Richard Resnick, so I'll not add to that and leave that to my colleague Steve DeWerth to introduce him. Steve, as many of you know, joined the Khalifa faculty in 2010, and he chairs our Department of Biomedical Engineering. I think he arrived a month before I did, if I recall correctly, so he has seniority over me. But he's done a marvelous job, obviously, in his role, not only in founding the BME program here, recruiting the faculty for that, but I think, as many in the room will know, we've been in the planning phases as a university for our College of Medicine and Health Sciences, and Steve has really been an integral contributor to that. He came to us from the joint faculties of Georgia Tech and Emory, which established the BME program there, and brings a wealth of experience in designing both educational and research programs in the biosciences, broadly speaking, to this task. He's been a great colleague and is much better technically able to introduce the speaker than am I. So it's a great pleasure to introduce Steve DeWerth, who will both introduce the speaker and moderate the discussion afterwards. So Steve.
Thank you, President Larson. It is indeed my great honor to introduce Richard Resnick, our distinguished seminar speaker. Richard is a pioneer in the rapidly growing field of genomics and is a lifelong and consummate entrepreneur. He received his bachelor and master's degrees in computer science and has an MBA from the Sloan School at MIT. He's been involved in the genomics revolution since its early days in the Human Genome Project with Eric Lander at MIT. Since then, he's had extensive experience building and growing innovative technology companies in the life sciences. Since 2008, he's been the Chief Executive Officer of GenomeQuest, a leading bioinformatics company that brings genomics to the life science industry, from hospitals to pharmaceutical companies to the agricultural industry. And I have to say, on a personal note, we've had a wonderful couple days with Richard on campus, meeting with the biomedical engineering faculty and with our colleagues, and it's been a thrill to be able to talk with him and to really hear his insights on entrepreneurship, his insights on where the genomic revolution is taking us, and just to get to better know one of our colleagues who's played such a seminal role in moving our field forward. The field of genomics is set to change the world through technological advances that parallel those of the microchip, the personal computer, and the internet. Mr. Resnick's record as an entrepreneur and as a genomics pioneer has given him a unique perspective in the future of this industry. We're honored to have him share those insights with us all tonight. So without further ado, I would like to invite Richard Resnick to the stage to wake us all up to the genomics revolution.
Thank you so much, Dr. Steve. We have a touch less volume here. Well, with introductions like that, it's hard to go forward. I think I can only rival the introduction with my greatest compliments to Khalifa University for the amazing 2 days that I've... Give us 1 second, please. Try again. Maybe I'll start here, yeah? I tend to like to walk around. Hope you can see me. I am standing up. The past 2 days have been a whirlwind for me, and I've had the luxury of having been able to brought my wife, and the two of us have experienced Abu Dhabi for the first time, certainly not the last. I am amazed at what you've done with Khalifa. You've grown up a university out of nothing in a matter of a few short years, and I'm so impressed with the biomedical engineering department and the staff at large, the Distinguished Speaker Series, and really honored to have a chance to speak with you all, so thank you. So, am I still stuck here at this podium? Yeah? This is James Watson, Francis Crick. You know these people. These are the guys that discovered the three-dimensional structure of DNA, the double helix structure, back in 1953. So what they essentially uncovered is that there is an instruction set which is given to each of our cells that tells our cells how to be, how to do, how to take shape, and what to do. So I'm here to talk to you tonight about how this very simple idea is about to change the way, and in fact in many ways already has changed the way that our society works. So here what you see is the human genome. 23 chromosomes, 22, and they're just sort of ordered. Number 1 is the biggest one, top left, and 22 is the smallest one, right there. And then these are the so-called sex chromosomes. X and a Y means that this is a male. It would be 2 X's if it were a female, so the X is a long chromosome and the Y is a short one. Now, if you zoom in, what you see, of course, is that double helix structure that I described. And looking closely at it, we all know about these, hopefully some of us know about these bases. There's 4 different letters in the book of DNA: adenine, cytosine, guanine, and thymine. And you can see that they're sort of spelling out these long words. The other thing I'd like to point out is that wherever on one strand of DNA you see an adenine, right opposite you will always see a thymine. A goes with T. And wherever you see a guanine, right opposite you'll see a cytosine. G goes with C, and vice versa. And this will become important later. So how big is this genome? It's huge. It's 3 billion bases big. Now to give you a sense of because people throw around numbers, a $3 billion project isn't such a big project, is it? So 3 billion bases when you're thinking about a genome. If you could take each one of those letters and make it be 1 dot on this screen, then we would need 3,000 screens to see the genome. So it's big, it's really quite big. But I get ahead of myself, so let me back up a little bit because I do want for you to understand some of the basics of the biology that the genome guides. Now, what you're seeing here is anybody know? the biomedical engineering students that I talked to today, they know for sure. This is a protein. I've been given advice that I'm going to try this again. Please hold. Can you hear me? Ooh, not so bad. A little lower, a little lower, a little. Still? Ah, so much better out here. Thank you. This is hemoglobin. So hemoglobin is a protein that carries oxygen in your blood. What is a protein? It's nothing more than a three-dimensional structure made up of amino acids, a series of amino acids. And in this case, this three-dimensional structure, if you look very carefully at it, it has 4 different groups here. These 4 groups are called heme groups. And if you look even more closely, right in the middle of each heme group is a little yellow dot. And that is an iron atom. So, believe it or not, this protein is designed to carry oxygen through your blood, and it does so by placing one small iron atom inside of each of these heme groups. What happens when you mix iron and water? You get rust. Iron, it's not really water that's doing the rust, it's oxygen that's doing the rust. There's an attraction between iron and oxygen. And that's really what's going on here, is that the oxygen that you breathe in, it oxidizes iron and moves about your body. And it's this mechanism that allows us to get oxygen to our most distant extremities. So, what's a protein? A protein is a string of amino acids, like I told you, right? How many amino acids are there? There's 21. And here they are. Here's the list of them. You don't need to understand what each of them are. But why is it that there are 21 of these? What does that mean? And what are their different functions? So the first thing that you need to understand is that some amino acids are positively charged. They have a positive electrical charge. And others have a negative electrical charge. And others are uncharged. And others like to be near water. They move towards water. And others are hydrophobic. They move away from water. So if you can imagine for a second that a protein is nothing more than a string of these, nothing more than just a series of these, and you've got some positively charged amino acids and some negatively charged amino acids over on this side of the string, you let this protein go, and what will happen is electrical force will bring these two things together. And if you have another one here that's positive, it will move away from a positive charge and towards negative charges. And the same with water-loving and water-fearing amino acids. And it's nothing more than the careful arrangement of these amino acids in a sequence that creates the shape of proteins. And the protein shape is the only thing that makes it useful. The shape of the protein, the structure of it in 3 dimensions, is what creates its function. So a protein can have sort of an opening here, and another protein has a perfect, like a key going in a door, fits it perfectly, and causes this protein to shift a little bit, which opens something else up. And this, my friends, is life. This is how we work. It's nothing more than this. We are proteins, and those proteins are strings of amino acids, okay? So, the book of DNA tells our cells how to make proteins. I told you before that there are 4 bases, G, T, G, C, A. So it's those 4 letters over and over again. This is DNA. And every single cell in your body has a whole copy of all this. The way that we make proteins is this DNA gets transcribed into RNA. It's exactly like DNA, except it's a very small message that encodes exactly one protein. You will notice, if you're looking carefully, that the only difference between DNA and RNA is wherever there's a T in the DNA, there's a U in the RNA. So there's a 5th letter, and it's only in RNA. It's called uracil. Don't worry, it acts just like T. Okay? Now what happens is that proteins are encoded in the following way. 3 of these bases, 3 of these letters, encodes for 1 amino acid. It's almost like a computer program. It's so simple, and it's quite amazing that it works this way. But this is how we make proteins. So proteins are encoded for by strings of letters in DNA. And the sequence of the specific amino acids, represented here by their own language of 21 letters, is what makes the shape of proteins. Don't worry about the complexity of this picture, but understand, just by looking at it, how complicated it gets from there. DNA, the thing that has the whole book, everything that's written about how all of the proteins exists in the nucleus of a cell. There's your DNA right there. Okay? And inside of the nucleus of our cell, DNA is turning into RNA. And this little ribbon is a specific message that was copied off of the DNA, and it's RNA. It's all of the instructions to make one protein. Okay? And over time in the cell, these things are proliferating. They're growing inside the cell in the nucleus, and then they get released. Little messages. These are just little notes, like telegrams to the cell to make this protein. One copy of this molecule here will make exactly one protein. And it works just as I've told you in the following way. The message enters here. It goes through a little machine called a ribosome, which is a protein, because just about everything is. And it takes 3 letters and it turns out an amino acid and creates these complicated proteins. And that's all it is. Okay? So this is how life works. And that's probably as technical as I'll get looking at the deep biology. But it's important to understand that the central idea behind molecular biology, which is what I'm talking about, is that DNA codes for RNA and RNA makes proteins. Okay? So this is what we call a codon. It's a 3-letter note. And AAA in DNA stands for one of the amino acids. And I can't tell you that I know which one. But if you sort of enumerate all of them, right, you say, well, keep these two the same. You've got the A, and then you go to the C, G, and that should be a T, excuse me. And then you do it again for the next. And you just sort of enumerate all of these different positions. Well, how many different codes are there? You've got 3. Right? 3 different spaces, and you can have 4 values in each of the spaces. So if there's any mathematicians in here, you should know that the answer is 4 to the 3rd. So there's 64 possible codes. But I told you that there's only 21 amino acids. So I've got 64 things I can say, but there's only 21 things that I can map that to. So what that means is that there are some codes like these here, CTT, and CTC, that make the same amino acid. You see? There's sort of a duplication. There's some loss of information there. And what's really important about that is that if there were a mutation, let's say, in your genome that changed a CTT to a CTC, it wouldn't matter. It's a safe mutation. It doesn't matter at all. But if the CTT changed to a CCT, then you've moved from leucine to proline. You've moved from this amino acid to this amino acid, and something bad is going to happen. What's going to happen is that the protein won't take the same shape that it was supposed to. And sometimes that matters, and sometimes it doesn't. So this is the idea behind DNA and mutation in DNA. Because of all of this sort of weak understanding of how this worked back in the 1970s and 1980s, we had sort of a telescopic view of the genome, but not a really fine-grained view of the genome. And so a group of very smart people got together in Alta, Utah, I think in 1983 or 4. And if you look and know anything about this industry, there are some names that still prevail today, like Lee Hood and George Church. And what they said was, is there a way that we can actually sequence the genome from one end to the other? Can we look at it from one end to the other? This is back in the mid-80s. So I'm going to tell you the answer was yes, but only because of a couple of amazing ideas that individuals came up with. And I'll back up and ask you to think about, why is DNA double-stranded? And there's a hint in the picture. This is a nice double strand here, and then it's split open, and look, there's a bit of it that's double-stranded again. So it looks like Maybe it's double-stranded because it allows for replication. You can make things single-stranded and then make them double-stranded again, right? So that's one idea. And the other is there's some error correction going on, right? You know, if you've only got one strand, you can make two. That's true. But you've got sort of the same message twice. It's like a backup on your hard drive in some way. Indeed, this idea works. If you take double-stranded DNA, like what I've got here, and you increase the temperature, it will split open, and you'll create two different strands. This works. So now I've got two strands of DNA. This man is a genius. This is Kary Mullis, and he knew about this back in the 80s. At the time, he worked for a company called Cetus Corporation. And he had this idea that has come to be known as PCR, or polymerase chain reaction. And this is a central technology that drives everything that we do in genomics today. Okay, so here's how it works. I've got a piece of DNA, just one copy of DNA. This is a very small molecule. You cannot see it in your hands. It's tiny, right? And what he knew was that if you heat it up in the presence of heat, that bond just disappears. And now you've got two single-stranded pieces of DNA. Now, you can take another